So this video will be on evaluating limits analytically, aka algebraically. So when evaluating a limit at a continuous point on the graph, direct substitution is a method for evaluating. So anytime that you are evaluating a limit, like in the previous video, I kind of jumped right into factoring. Just use direct substitution first. There's so many instances where I saw students, they could just directly substitute the limit they are evaluating and get the answer, but instead they use another method when they do not have to. So direct substitution should always be the go-to. So let's start with this one. The limit as x approaches pi over 3 for sine of x. So let's use direct substitution. So sine of pi over 3. Make sure you have your unit circle memorized. If you don't, go back and do it. This is in quadrant 1, closer to the y-axis. Therefore, that means we have root 3 over 2. All right, the limit as x approaches 2, direct substitution. So 2 over 2 minus 3, we end up with negative 2. The limit as x approaches 2.5 for the step function. So if I plug in 2.5, so thinking back to the step function, remember 0, 0 is a point, right? And then I use a different color. And then from here, it just looks like this, okay? So if we think about 2.5, I have 0. This is 1, 2, 3. 2.5 is going to be located on this third bar here. Not third bar, that's horizontally. So this is 1, this is 2. Because I have to remember, limits go to y values, not x values. Well, they approach an x value, but they should be evaluated using the y values. So that means this will be equal to 2. All right, so there are various techniques that we will be using throughout this course. The first technique, dividing by a common factor, we already did that in this example up here. The last two examples where we saw some removable discontinuities, aka those holes, okay? So that's the first technique. The second technique is going to be simplifying complex fractions, and then if you want to read through these descriptions, you can pause the video, but that's what we're going to be doing here. So the limit as x approaches 3 for this complex fraction. The first step is use direct substitution, all right? So if I use direct substitution, I get 3 plus 1, so that ends up being 1/4 minus 1/4, which is 0, divided by 3 minus 3, which is 0. So we get 0 over 0. We will have another method for solving this. It is called the indeterminate form, but so far in the course, we don't have the methods in order to solve this. Honestly, the method we do today is probably a little bit quicker, but you will have multiple ways to solve these problems, okay? All right, so we tried direct substitution. It did not work. All right, so the first thing that you want to do is you want to simplify this fraction, and then eventually we need to try and get rid of this x minus 3 in the denominator, and the best way to do that is to come back to technique 1 and divide by a common factor. Okay, so let's see if we can get there. First off, let's go ahead and create a common denominator for the numerator. It is 4 times x plus 1, so we will multiply both of those with 4 times x plus 1. Now, we can't just multiply this with 4 times x plus 1. We are changing the value of this function. So how do we keep it the same? By multiplying it by 1. So we'll do 4 times x plus 1 divided by 4 times x plus 1. This is equal to 1. So essentially, we're multiplying this function by 1, so we're not changing the value or the weight of this function, okay? But now we have a way to combine the two terms in the numerator so that we can simplify this, okay? So what I'm going to do is I'm going to take this 4 times x plus 1, multiply it with the numerator of the first fraction, and then take it again, multiply it with the numerator of the second fraction. Then I'm also going to take this denominator and multiply it with this binomial. All right, so let's see what happens. So we have the limit as x approaches 3. Do not forget your limit, all right? The limit stays in every single step. I have people that ask this, can I draw an arrow? No. You write it for every single step. Don't be, okay, in calculus, we try to be lazy. Like we try to use the method that works the quickest and the simplest, but as far as notation, there's no shortcuts for that. So the limit as x approaches 3. So I'm gonna show every step just because some of you might be learning this for the first time. No, actually you're not, but in this course you are. So 4 times x plus 1 divided by x plus 1. Minus, we have 1 times 4 times x plus 1 divided by 4 all over, we have our x minus 3, and then we have the 4, and then we have the x plus 1. So if you need a second to see what's happening, pause the video, okay? But I'm going to keep going. Now from here, in this first term, we can see that the x plus 1's cancel out. In the second term, the 4's cancel out, okay? So we have the limit as x approaches 3. We end up with 4 minus x plus 1 all over. I'm going to move the 4 to the front just to clean it up. 4 times x minus 3 times x plus 1. Okay, so we are simplifying this. We no longer have a complex fraction, it's just a fraction now. But the goal is we are evaluating the limit as x approaches 3. This binomial is going to be a problem until we get rid of it, because whenever we directly substitute that 3 in, we're always going to get a 0 in the denominator. So we need to find a way to cancel that out. So if we look at the numerator, stay consistent, the limit as x approaches 3, if we manipulate this, we end up with 4 minus x minus 1, all right? So this just turns into 3 minus x, all over 4 times x minus 3 times x plus 1. All right, so I'm working with the new similar numerical values that are to this binomial, but I need the x to be positive and I need the 3 to be negative, all right? So in order to make this happen, the limit as x approaches 3, I'm going to factor out a negative, so I end up with x minus 3 divided by 4 times x minus 3 times x plus 1. Now from here, we go back to technique 1, which is canceling out a common factor, okay? So we'll have the limit as x approaches 3, we'll have negative 1 divided by 4 times x plus 1. Okay, so the original headache was that x minus 3 in the denominator, but now it's no longer there. So let's use direct substitution and evaluate this. So we have negative 1 divided by 4 times 3 plus 1, which means we get negative 1 over 16. So at x equals 3, this is a removable discontinuity, a hole. If it was a vertical asymptote, it would have been infinity, or it would have been does not exist, okay? All right, the third technique is going to be rationalizing, all right? So if we take a look at this, we aren't dealing with a complex fraction. We don't have a common factor that we can divide out. So we're going to have to use another method. Basically, what we want to do is simplify the numerator by rationalizing. So we're going to multiply with the square root of x plus 3 plus the square root of 3. And we do this in order to cancel out a few things. Not a few things, but to cancel out the square roots in the numerator. Now, same thing, I can't just multiply whatever I want with this. I can only multiply it with 1 because I do not want to change the weight of this function, okay? So we're going to multiply with the conjugate. All right, so when we double distribute, this worries me because I understand that I need to show these steps, but you guys need to make sure that you're practicing outside of class and outside of watching these videos. You have to actually practice problems on your own so that you can understand what's happening with these. Within the numerator, we're going to double distribute, all right? So square root of x plus 3 times the square root of x plus 3, that's going to result in just x plus 3. Next, we have the square root of x plus 3 times the square root of 3. And then after that, we have negative square root of 3 times the square root of x plus 3. Those two terms are going to cancel out. The first one was positive, this one is negative, so they always cancel out. This is why we use the complex conjugate, because it simplifies the numerator and it gets rid of the square roots in the numerator as well. So now we have negative square root of 3 times square root of 3. That's going to be minus 3. Denominator, we have our x, and then we have our square root of x plus 3 plus square root of 3. All right, so in the numerator, we have x plus 3 minus 3. That just becomes x divided by x times the square root of x plus 3 plus root 3. So just like in the previous one, the problem with this one is the fact that x is approaching 0 and it's in the denominator. But now we can go ahead and cancel that out. So we have the limit as x approaches 0 for 1 over the square root of x plus 3 plus the square root of 3. Since that x is out of the denominator, let's try direct substitution. Once you directly substitute, the limit goes away. You are now using that limit, so it's no longer in place, okay? So we have 1 over the square root of 0 plus 3 plus the square root of 3, which is equal to 1 over 2 square root of 3. On the AP exam and in class, once you apply the limit, you can stop here, all right? Or you can go to here. And if your heart desires, you can multiply by root 3 over 3, but you are not required to do all of that, all right? So when you are taking an assessment or you're on the AP exam, not doing things like this can save you a few seconds. Those few seconds add up to minutes that you could utilize later on a more difficult problem, okay? So just keep that in mind as you go forward, that simplification is not required unless it's specified, okay? All right, so the last part of this is limits that fail to exist. So the first one is differing right and left behavior. So I'm just going to draw a quick discontinuous piecewise. So let's say that we have a parabola, or just a curve here, and then another curve just above that, okay? And we'll call this C. So if I want to evaluate the limit as x approaches C, we'll call the function f of x. The limit from the left has to agree with the limit from the right, aka they need to approach the same y value, all right? So if we look at this, this is a y value that is less than the y value that is up here. Therefore, the limit does not exist. Now, someone in class asked a really good question. They asked, okay, if the limit doesn't exist, do we have to show that it's this from the left and this from the right? No. We will never trick you, all right? If we want you to justify why it doesn't exist, we will explicitly ask that, okay? So if you are evaluating a limit and the left and right do not agree, it is simply does not exist. Unbounded behavior, this is going to be asymptotes, okay? So if I have a curve where it's going to infinity on the right side and then maybe negative infinity on the left side, we can say the limit as x approaches C, C will be the asymptote for f of x. Well, the left and right do not agree, so this will be does not exist. Now, what if we change this up a little bit? What if we do, they're both approaching positive infinity? All right, well, the limit as x approaches C for f of x, this will have two answers. It could be infinity or does not exist, all right? And the same can be said for negative infinity. If both sides are approaching negative infinity, the potential answer could be negative infinity or DNE. It's all about what's happening from the left and the right side. Oscillating behavior, I had a good question about this in class as well, and I'm going to try and research it a little bit more. However, we use sine. Sine oscillates between -1 and +1, all right? And because of this oscillating behavior, the limit is not approaching a single or an individual y value, all right? So this would be does not exist. Now, we also have oscillating functions that do this. They do get closer and closer and closer. But if I were to zoom in again on this, it would still look the same. But then it get closer and closer again. But if you continue to zoom in on that, you will still see it oscillating. So the question in class was, okay, it's oscillating, but it's still approaching a value. And we're going to talk about this more as we go forward, but if you think of an exponential function, let's say exponential decay, it's decreasing, but it's approaching that y value from the same side infinitely. With the oscillating functions, it's passing through, it's equaling, and then it's not. And then it's so with this erratic behavior, we say that oscillating functions, the limit does not exist. However, for exponential functions, we can say that it does exist because it's approaching that asymptote. So I'm going to research more, and we'll talk more about it in class, but some really good questions occurring. Okay, if I don't know an answer to something, I'll do my best to try and find it. Okay. All right, number 11, the graph of f of x is equal to this piecewise function. Now, we do have a removable discontinuity. We can see that we have two factors that cancel out. So we'll have a removable discontinuity at 2, and this is a parabola. Now, the second piece is at x equals 2, we have a value of 6. Okay, so we'll go ahead and mark. And I want to go ahead and note the output for the removable discontinuity. If I plug 2 into x squared, I get 4. Okay, so part A, the limit as x approaches 0. First step, direct substitution. I have 0 squared, which is equal to 0. Because the simplified form for all values except for x equals 2 is just x squared, because these factors cancel out to create that removable discontinuity. Same thing for 1, direct substitution. I have 1 squared, that's equal to 1. This should say 2, the limit as x approaches 2 for f of x. Now, try direct substitution. If we remove those two factors, the x minus 2 over x minus 2, I get 2 squared, which is equal to 4. Again, limits do not care what's happening at 2. They only care about what's happening around 2, and they are approaching y equals 4. And then f of 2, this is different. This is not a limit. This cares about what's happening at x of 2, which means it is going to be 6. All right, that's the end of the limits. I hope this was helpful.